Thank you, thank you. Well, it's very nice to be here, thank you. Yeah, my background is physics, and I'm Irish, so sometimes I might switch into speaking in Irish or speaking in physics, so you have to give me some credit for that, or give me some space with that. So I have some notes here. What I'm trying to try and do, I'll pass the notes out, and these are also on the website. What I'm trying to do is to sort of fill in some of the details of what Jeff was saying, in particular about the connection between the way in which one can construct modular forms in a very natural way using the axioms of vertex operator algebras. And so I'm going to start by doing a little bit of elliptic function theory, and because elliptic functions also play a role in this whole game, and use that as a motivation and as a way of establishing some of the notation, some of the ideas I'm going to need. And also use that as a way of describing modular forms, just the modular forms that will appear. And then I'll move on to review the axioms of VOAs. The language is pretty much the same that Jeff used, and there'll be some small differences here and there, and I'll try and remember where they arise. And then I'll show you how, from working with trace functions, Jeff talked about the partition function, and also described, I think, the one-point function briefly, I think, is that right? Yeah. So I'm going to talk more about that, and how you can actually just, using the locality axiom, construct modular forms, or more generally elliptic functions from vertex operator algebras. This is a very natural thing, and okay, there's lots of indices and things flying around, but the actual basic ideas are not so difficult. And it turns out the basic result that one gets then is very powerful, because it allows you then to discuss modularity, domains of convergence, and things of this nature for these one-point functions, or in general, endpoint functions. Okay, excuse me, I've got a cough. Okay, so let me begin then. So in the handout then, I've fleshed out some details I'm not going to necessarily talk about completely here, and so I'll refer to the handout every now and then to say, look for the more details here. So let me first of all talk about some elliptic function theory. So at the end of every class I give back home, right, when I get the forms back from the students, they tell me my handwriting is terrible. So I will try and write big or something, so my handwriting won't be so illegible. So let me talk about, first of all, I want to, before I go anywhere, get some notation straight. So throughout the whole talk, when I speak of a variable z, it'll normally be in the complex plane. Occasionally it might be formally a number, but for the first part of the talk, it'll be certainly a complex number. And a variable tau will be in the upper half plane. And I'll also introduce the notion of, or the notation qz, which is just a shorthand for the exponential of z. And q, well, it's actually q of 2 pi I tau, which is the exponential 2 pi I tau, which I'm just going to call q. Okay, so throughout the first part of the talk, these variables qz and q are going to appear all over the place. Okay, so let me first of all define what's the classical object in elliptic function theory is the Weierstrass function. Okay, it's defined in the following way, at least for my purposes. It's a function of z and tau, and I'm sure many people have seen this before, in some shape or form. Sorry. And the following. Okay, and what's omega? in this talk, omega is going to be 2 pi I into m tau plus n. Okay, so this clearly function is z in tau. And this prime here denotes the fact that the value is n equal to 0, 0 is emitted. So denotes, this is the singular value of the right-hand side here. So this little factor here is designed to make the whole thing absolutely convergent. So this is a function which is analytic in Z and on the whole complex plane, and it has a pole of order 2 at every value of omega n. So it's pole for all mn. Okay, so it's a classical fact that and this was it's clearly it's defined on analytic on the whole complex plane, and it's periodic. Periods 2 pi I and 2 pi I tau. So some of you may have seen this thing written down before. It's just convenient to use these periods 2 pi I and 2 pi tau for the purposes of later expressions. It makes it easier to write things down. There's not factors of 2 pi I all over the place. They appear here for the time being. And so the following property. So that's just a trivial fact from the way in which the thing is defined. Okay, so the classical result in elliptic function theory is that basically all elliptic functions can be expressed in terms of this the object here and its derivative. Okay, and you would know about the famous cubic equation that relates those together. Okay. What's I want to say next? Okay, so it's an elliptic function. Oh, sorry, thank you. Exactly. Thank you. So this is, by definition, an elliptic function. And so we can think about this function as existing on, oops, sorry. Well, okay. Define a fundamental parallelogram in the complex plane with vertices given by this. In this parameterization of 2 pi I, 2 pi tau. And the fact that the function is periodic means that the value of this edge here is the same as the value of this edge here, and this edge here, and this edge here. So I can really think of this function as living on a torus. Okay, that's what it means to be an elliptic function. So, and there's a little picture shown there to indicate that. So this is the same as a torus, basically. We're identifying the opposite edges. So as an elliptic function, it lives on the torus. And that's the whole point of, that's the whole setting in which these one-point functions and partition functions are going to be discussed. There's something associated with a torus. Okay? And what Jeff talked about in his seminar, I guess, was how we're trying to push this beyond the Riemann surfaces of higher genus, where you have more holes, a donut with several holes. Okay, now, just a little bit of notational aspects again. Okay, sorry, the torus, of course, can be thought of as being the complex plane and quotient by a lattice, and the lattice is generated by, in this basis, 2 pi I tau and 2 pi. Okay, so you can imagine, sorry, what I mean is the set of all points m 2 pi, well, it's written there a moment ago, omega mn. Okay, that generates a lattice, and so this identification is the same as what I was talking about a moment ago. Of course, you can choose different bases for this lattice, and the choice of different bases corresponds to making some kind of choice of different generators for the spaces. And when you do that, then that corresponds to what's called a modular transformation. I'll come to that in a moment. Right. And yeah, I want to say one other thing, which I'm going to put up on the board here as well. For this parallelogram here, it's called the fundamental parallelogram. And it's an easily demonstrated fact, so that if I consider a point in the fundamental parallelogram, we have minus, where is it? 2 pi the imaginary part of tau is less than the real part of z is less than 0 when you're on the fundamental parallelogram, and that corresponds in terms of these variables here to the constraint that, I always forget this, which around it goes, that q is less than qz is less than 1. So for the first part of the talk, I'm going to spend some time explaining how this Weierstrass function can be written instead of in terms of these standard variables in an alternative way, if you want, in terms of sort of Fourier transform variables, q and qz, which perhaps is less familiar to some of you. So I'll spend some time doing that. And the reason we do that is because the expressions we write down in terms of VOAs are naturally expressed in terms of q and qz. Okay, so they'll be the natural variables to describe things on the torus. Now let me talk about modular invariance. So there's a natural action of the modular group. Oh, this board doesn't move. Okay. Oh well. Has a natural action on, which one does I write it here? C cross H as follows. If I take gamma equal to A, B, C, D, we saw this written down several times yesterday. So A, B down to D are integers, of course, and the determinant is equal to 1. Then we have the following natural action where gamma of z tau, is as simple as gamma z gamma tau is z over c tau plus d into a tau plus b over c tau plus d. Okay, so it's easy to check that that's a natural action on the space. And the meaning of the modular transformation is such a modular transformation corresponds basically to a basis change in this lattice. And so we're still describing the same torus under this basis change. So this corresponds to a basis change for the lattice. Again, I'll just make sure I get this right. So 2 pi I, I've written here is tau, and 1, so 2 pi I, so a tau plus b to c tau plus d. Okay. So this forms an alternative basis as long as the determinant of a, b, c, d is 1. And so when you make this basis change, the second parameter is no longer 2 pi I. So when you rescale, that's a conformal rescaling, as it's called, we send z to z over c tau plus d. Okay, so that then, so it's like scaling up the whole parallelogram if you want. So I can take this parallelogram, perform my modular transformation, and then you scale everything so this lower edge here is 2 pi I, normalized to 2 pi I. So under that transformation, it's very easy to see this function here has nice properties. Okay. So when you make a modular transformation, the z gets scaled as I said here. And the basis change just means I'm changing the way in which I describe omega n, basically, but it's the same sum. And so at the end of the day, this thing here is modular invariant up to a scale of c tau plus d squared inverse, coming from the overall one of the z squared pieces here. So it's very easy to see the following. Under this modular transformation, you can do this as an exercise if you want. Okay, just quoted there. A p of gamma, z c tau plus d squared p z tau. So the Weierstrass function behaves in that way under a modular transformation. Okay, sometimes you see the Weierstrass function expressed in terms of an arbitrary basis. Some of you may have used that omega 1, omega 2. And then you don't see this scaling factor here. But the fact is I'm choosing my description so that the lower part of the lower edge here of the fundamental parallelogram is always 2 pi I. And that's where that extra factor comes from. It's just to do, if you want, for a physicist, you say the thing has dimension, length dimension minus 2. Okay, so the whole thing's been rescaled. Okay. Now what I want to do next is to point to the following facts. In particular, notice that, and this goes in with remarks that Jeff was making before in his talk, I think, that if I choose gamma equals to t, following matrix, which corresponds to t sends tau plus 1, well, that matrix there has c equal to 0 and d equals to 1, and so the function is, in fact, invariant under this transformation. Okay. Tau plus 1 is tau. But we also had the periodicity equals 2 pi I. Okay. So very naturally, then, one expects that this Weierstrass function should have a Fourier expansion in both the variables q and qz. All right. So this thing, we should be able to give this a Fourier expansion in q, and this implies Fourier expansion in qz. These variables here I defined up here. Okay. So that's what I want to do next. I want to spend a bit of time, because this is standard stuff, but you'll find it in lots of books. But it's kind of, rather than throwing it at you, I'll spend a little bit of time just explaining how that works, and the details you can find in the notes. But it's kind of fun, and it's very beautiful what the formula actually is for P. The other point is then that it's these variables that naturally arise in the conformal field theory setting, in the VOA setting. And so we want to find expressions for elliptic functions in terms of these variables q and qz. Okay. So let me give you the following. What I might do is kind of give a compression of some of the formulas that appear here, and then I'll fill in some of the details. And let me define the following. So let's define. Now the notation might seem a little bit peculiar, but let's just stick with it. P2 of z of tau as the following sum. It's n qz to the n over 1 minus q to the n. And I'm also going to define, I defined it in the opposite order in the handout there, P1 of z, which is this related sum when I have qz here. Minus q to the n. And for slightly technical reasons, I need to add a constant here as well, that I'll explain in a moment. Okay. So this is actually equal to P1 prime, where the prime refers to a z derivative, sorry. Let's call that d by dz. I guess it should be a partial derivative. Okay, so what I'm going to show you now is that the Weierstrass function is given by P2, but you have to add a correction. And the correction term is this famous Eisenstein series E2 that some of us like and some of us don't like. Yes, so let me define the following thing. E2, I'm going to define it in a slightly peculiar way, but it's sort of natural in this context. M, and it's a nested double sum. When I define the Weierstrass function here, it's absolutely convergent. That's the purpose of this term here, essentially. So it doesn't matter the order in which the summation takes place. For this function, the order of summation matters, and so we get a different answer if you interchange the order of summation. But it certainly converges. And again, this should be a prime here, meaning I leave out the value 0, 0 for m and n. So we define these various functions of q and qz, and if I define E2 in the following way. And this is a function of tau. Okay, so then we have the following proposition that the, well, I don't want to write this. P2, this nice expression in terms of qz and qn, is the Weierstrass function plus E2. Okay. So I'm going through all this trouble because it's in this form that the elliptic functions arise in VOA theory. So now, it's not very difficult to prove this, and what I'll do, I'll just sketch the way this works, and you can read the details in the handout there. So I've tried to make the handout reasonably complete. are internally complete anyway. Of course, there are lots of issues I'm not talking about, but most of the details are actually shown there, I hope. Okay, so in order to prove this thing, you need a little classical lemma. You'll find this again all over the place. I think it's even in Whittaker and Watson and old books like that. If I take the following sum, z, well, this is the same as qz, or qx, sorry, over 1 minus qx squared. And of course, qx, again, I'm using this notation that's above there, exponential of x. So this is related to a tanh function. If you rewrite it as tanh of x over 2, I think. Or sorry, it's what is it? Sech squared of x over 2, isn't it? Yeah. No. Forgetting what I'm doing. It's 1 over the shine squared of x over 2. Something like that. Anyway, so you can compare the pole structure on either side. And this function has poles of order 2, 2 pi n, and so forth, and you can work out that this indeed so that's an exercise I think I gave you. So using that simple idea, it's possible to compute this inner sum here. Okay, if I reverse the order, then this doesn't work. But I can compute the inner sum here, making use of this ordering of q and qz, in which these whole things are defined. Then you end up with this expression here. So, yeah, I think I'll leave that there for you to read for yourselves. Okay, it's very straightforward. You just use this expression with different choices of x. Okay, in particular, well, I can start you on the road. If I take n z of 1 over this term here, omega squared. Well, sorry, before I go further, let me. So how do I make this relationship between curly p and capital P? Well, this nested sum here allows me to actually write p curly p plus e2 as a single sum. So then use curly p as the tau plus e2 is the same as the following single nested sum. Okay. And I'm no longer excluding m and n equal to 0. So if you remember when I wrote the p function down, I had sort of 3 separate terms. Well, and then if you include this e2 factor here, well, e2 factor is like the third term I had in a formula for curly p. And by writing it in this nested way, I have an expression for p curly p plus e2. So then I can compute this sum here by this lemma. Okay. And then when you chase through the whole thing, making use of this ordering here in the variables, you get the answer. Okay. So it's not hard to see that when you use that lemma there, you end up with this formula. Okay. So that's very nice. So we have a very beautiful expression for the Fourier transform. Sorry, written in Fourier variables for the Weierstrass function. And along the way, it's sort of it's natural to introduce this E2 function. Okay. So the Weierstrass function is a unique function with a pole of order 2 up to an overall constant, additive and multiplicative constant. So if you want, I'm choosing the additive constant to be E2. And then you get a more natural expression for the Weierstrass function. Okay. There are some other reasons why I want to do this in the VOA theory as well that I may have time to come to. Okay, so now how does all this relate to modular stuff? Well, let me now consider, I'm going to expand my Weierstrass function as a function of z, and identify the coefficients, and the coefficients are Eisenstein series. Okay, so consider, so now I come to the part which contains modular forms. Oops. You can consider the z expansion of, well, I'll write it as p of z tau plus E2. And you expand that out. So easy to see. This is the same as 1 over z squared plus, and then we have the following sum, k minus 1 equals 2 to infinity of e k of tau z to the k minus 2. So it's an even function, and I'm including here k equals 2, so I have the e2 factor included in this sum, where ek tau is, when you work it out, is 1 over 2 pi I to the k, the sum of omega n. Sorry, well, it's omega n. Okay, I'll leave out that term. It's the same as m tau plus n to the k. And again, excluding the origin. Oops, sorry, that's nonsense. Mn, sorry. Mn and z, and excluding the origin again. And this is the Eisenstein series of weight k. This is called the definition of the Eisenstein series of weight k. It's easy to see if k is odd that for every mm, but you can also have a contribution from minus m, minus n, so it vanishes if k is odd. If k is odd. So it's only for, so ek is defined for k greater than or equal to 2 even. Sorry, is non-zero. But you can define ek if you want for k odd, it's just 0. So now, if you combine this expansion with the statement of modularity, which has gone off the board now, has it, for the p function, you immediately get that this Eisenstein series are modular forms, except for the famous E2 term, which I'm not going to discuss its modularity or prove it. I'll just state how it transforms. It's slightly more technical. So in particular, if I was to, okay, I've written this, so this is the same as, yeah, so I've written it here. It's pz plus E2, and this is P2, of course, is this thing here. So if I ignore the E2 term, then we have an expression, of course, for curly p, the Weierstrass p function. And so immediately from the modularity I discussed, modular property of the p function, I get that the Eisenstein series are modular forms. It's modularity of p, ek tau is a modular form of weight k for k greater than or equal to 4. Right. That is, if I take ek of gamma tau, it's the same as c tau plus d to the k ek. Right, so these things have appeared several times, I know, in some of the talks. By the way, I think I also was mentioned, I mean, there are various ways. So sometimes this is called gk. Sometimes the factor of 2 pi I k is missing. Sometimes you'll write 2k here instead of k, whatever. So there are different sort of conventions as to how one can write these things. But obviously, they're all the same up to various constants. Okay, but this is the convention we're choosing. And it's chosen because, in fact, the Weierstrass function is so naturally expressed in this simple way. And the object is a modular form. So when we come to do the VOA stuff, all the modular forms that arise will all be Eisenstein series. And there'll be a natural expansion of one-point functions in terms of these Eisenstein series. And they come directly from this expansion here. Okay. So this is kind of the heart of matters, really, from the point of view of the application we have in mind. Now you can take the Q, the Fourier expansion, alternatively. Again, this is explained in the notes. Alternatively, from the QZ Fourier formula for P2. That can be expanded also in terms of Z, and you get an alternate expression for these Eisenstein series. Okay. We find EK, there's a formula I can write down here. So again, that's explained on page 4 of the notes how this works out. And we find this is the strictly speaking, the only connection with the zeta function I'm going to actually mention is the appearance of Bernoulli numbers. 2 over k minus 1 factorial. So we get this, well, yeah, it can be expressed in various ways. So this is one way to write it. nk minus 1 over 1 minus q to the n and q to the n. So taking the formula I had for P2 expressed as a function of q, z, and q, by expanding out the qz's in terms of z, you can just read off the various terms, and then we get this expression here. And what's bk? I keep writing on the unmoving board. So bk is a Bernoulli number. QZ, and this is one of the terms in the expansion that we talked about. It's 1 over z squared minus the sum of bk over k factorial. And then we have this extra factor k minus 1, z to the k minus 2. This is for k even. Okay, so these are related, of course, to the values of the zeta function. The sum 1 over n squared, 1 over n fourth, 1 over n sixth, etc. are given by the Bernoulli numbers. Again, you can see that here, when you put tau equal to 0, that's the zeta function, okay, evaluated for integer k. Okay, so that's the connection of the zeta function as far as I'm going to use it. Okay, so lastly, then I didn't mention what happens to E2 when here this is for k greater than or equal to 4. So you may remember at the beginning I said when I wrote down the definition of E2 that it was a particular ordinal of the nested sum, and if you make a modular transformation, it corresponds to a basis change. So you need to be able to reorder the sum, and in doing so, the answer actually changes according to the order of summation. So you can read this in various places. Sarah's book, for example, on modular forms or Introduction to Arithmetic. So what one finds is that E2 of tau is what's called a quasi-modular form. So it has this extra term under modular transformation that E2 of gamma tau is c tau plus d squared into E2 tau. So far so good. It looks like a modular form, but then there's a correction term here which is very interesting and very important over 2 pi r. So you can talk about the ring of modular forms, and it has been mentioned several times before. In fact, E4 and E6 generate, if you take any modular form, it's going to be a polynomial in E4 and E6. And then you can extend that to this what's called quasi-modular forms, where you have this sort of extra sort of anomalous piece here. And then you have a ring of quasi-modular forms, which is generated by E2 and E4 and E6. Okay, so there's a kind of bigger class of gadgets than one can actually deal with. So I should just mention that. So so E4, E6 generate a ring of modular forms. Now I haven't even talked about what I mean by a quasi-modular form in general, but I'll just use that terminology at least anyway. And E2, E4, E6 generate a ring of quasi-modular forms. Okay. Now, E2 arises naturally in this whole game, as I say, if you want, even just aesthetically, if you want to actually write the Weierstrass function in its most refined way in terms of the Fourier variables q and qz, it's sort of natural to add the E2 function. But also in the conformal field theory in VOA setting, it's very natural that this E2 function arises. I think Jeff talked about that. In particular, it plays a really deep role in what goes on at genus 2. And the way in which modular group acts and all kinds of stuff. So it's very interesting. But I also want to mention, it plays another role, and which is related to all those things. E2 plays a role in defining a sort of covariant derivative. There's a sort of a notion of covariant derivative where you can differentiate modular forms and get more modular forms. And I'd like to mention that because that's going to appear later on. So we have a notion of, I think I call it the modular derivative here. An application of E2 if you want. It's called the modular derivative. So if I let Fn be a modular form of weight n, okay, so then I can define a sort of a covariant derivative or a modular derivative of Fn. Then if I take q d by dq, and I add a multiple of this E2 function, which I add the weight n, and act on f of n. And I'm going to use a shorthand notation, just call this thing capital D. Is a modular form of weight n plus 2. So that's a really cool thing. So you can actually take modular forms, differentiate them, essentially, and build up modular forms of higher weight. Okay? So again, that's left as an exercise. It's very easy to prove this. It's just an exercise in applying the Leibniz rule, essentially, and then using this extra piece here. So this piece here, if you want, makes up the deficit and what happens when you multiply the c tau plus d to the n term here. And then just touching again on our own research, recently we're sort of working with sort of a higher genus version of this, which is really very nice. There's a very nice sort of geometrical background to what this actually means. So it's been puzzling me for a long time as to what this actually really means. And I think I understand a bit better now in geometrical terms what that modular derivative actually is. But, so you have to kind of go to another picture. But anyway, so that's kind of a cool thing. And this is going to appear in some of our discussions later on. As an example, I have some examples here. So for example, if I take the modular derivative of E4, well, this is of weight 4. I'm going to get some multiple of E6. And it's written down here somewhere. It's 14 E6 in it. And if you differentiate E6, you get some multiple of E4 squared and so forth. That's confusing. Okay. So the exercise is both to prove this and to, if you want, work this out. Okay. One interesting example of this modular derivative is what happens if you hit the cos form 12, sorry, the cos form of weight 12 delta, which is eta to the 24, is a weight 12 cos form, which, did you define delta? This is defined a couple of times. Okay, so this is the same as q into the product over n equal to, greater than 0 of 1 minus q to the n to the 24. So it's 24th power of the eta function. So this thing here, you see as q goes to 0, it vanishes. So modular form in general will have a constant term, but this thing actually is a cusp form, these are interesting objects in their own right. And using that statement I made about being able to generate all modular forms from E4 and E6, it's easy to see that in fact there are no cusp forms of weight 14, and so necessarily then there's no cusp forms of weight 14. So this implies that when I apply the modular derivative to delta, it's 0. Okay, which implies in turn that if I apply the modular derivative to eta, it's equal to 0. Okay, in some senses that's maybe a definition of what eta is, or delta. Anyway, it's an interesting thing. Okay, and again, that's as an exercise, that appears in the notes. You can work this out for yourselves just by actually looking at what d of E4 is and what d of E6 is and working it out. Or you can invoke this more sophisticated theory of what the ring of modular forms actually is and how it's generated. Okay, so actually that's all I think I need now in terms of the theory of elliptic functions. So I'm slightly later than I expected to be. Oh no, I have one more thing to say. So because of the expression, its expression in terms of Fourier coefficients, if you recall, I also defined a function called P1. So let me come back to that. So I defined P1 as z of tau to be the sum, it's a slightly easier looking thing, simple looking thing, What was it? There's QZ to the n. Q to the n. And I have this factor of 1/2, I think. I did it like this. Okay, well, this is an odd function. In z, so that's the purpose of the constant there, is to make this odd in z. That's not hard to see if you just track it through. For given the additive constant. Okay, and this is a function of qz, so it's necessarily periodic in z. Okay. By definition. Okay. But it's not periodic in 2 pi I tau. So in fact, if you track it through more carefully, but I don't think the difference minus p1 of z of tau is actually equal to 1. So it's not periodic in 2 pi I tau. So this is not an elliptic function. This is related to the Weierstrass zeta function, different kind of zeta. Sorry, sigma function, the Weierstrass sigma function, if you're familiar with elliptic function theory. Okay, and so it's not actually an elliptic function, but nevertheless, all its derivatives are. But p1, the nth derivative, which means d by dm, is elliptic. Because the first derivative, if you remember, was p2, and that's an elliptic function. It's elliptic for n equal to 1. So when it comes to looking at the VOA expression for elliptic functions, everything's going to be expressed in terms of p1 function. Okay? But actually, only the derivatives of p1 will appear. Now, this is just a notational trick in some senses, but there may be some deeper aspects as well that I'll touch on. But everything is more easily expressed in terms of p1 rather than writing it as p2 with more factors of m around the place. So, that's which to say that the following statement is true. Well, okay, no, I'll leave it. That's fine. I'll leave it at that. So I will be using these functions later on when I write down expressions for one-point functions. And the derivatives of p1 will appear. In particular, the first derivative is p2. And so all I'm doing is invoking the standard elliptic function theory that the p2 and its derivatives are all elliptic. Okay? Now, they're not independent. And in fact, there are only two independent functions, p2 and p2 prime. But nevertheless, I will use this description of elliptic functions as they arise. Okay, so so in fact I will need the following expression too. So this is equal to p1, is the nth derivative. It's very easy to compute in terms of its Fourier coefficient. You just differentiate this formula here m times, and you just pull back down a factor of n. 1 minus q to the n. Okay, so p1 of m is this thing here, m equal to 1. So when we do the VOA manipulations, it's expressions of this kind that will actually arise, very, very naturally. Okay, so all of that was supposed to be kind of a warm-up exercise, or not, well, no, it's sort of setting out the notation. And so just to review, the main thing I wanted to say here is that there are elliptic functions that will arise in these calculations in VOA theory, and they're naturally expressed in terms of this basis. I've tried to indicate how these are related to the standard definition of the Weierstrass function. And also this modular derivative is going to play a role as well in things I have to say later on. And when you expand these functions here in a z basis, in terms of z, the coefficients are modular forms. So in general, if I expand this out, it's m factorial into minus 1 to the m plus 1. I did this I wrote this down a moment ago for m equals to 1, but in general, it's easy to work out these derivatives. And we get k minus 1, choose m. Okay. Plus 1 of ek. This is equation 17 in the handout. It's the k minus m minus 1. So there's a natural expansion of each of these elliptic functions in terms of modular functions. So the initial calculation I'll do in the VOA theory will be expressed in terms of these guys, and then when you do a specific z expansion, you'll identify modular functions. Okay. So now let me do a brief review of some VOA theory. And I'm going to try and highlight, I'll leave that up there, highlight some of the particular aspects of VOA theory that I'm going to use. Okay. So this, of course, is what Jeff was talking about the last few lectures. And I think the notation I'm using is slightly different, but I think we can live with that. And everything else will be the same, I think. So VOAs, what's a VOA? A VOA is this gadget where we have a vector space, V, some linear operators on this vector space I'll come back to. There's a particular vector in the vector space called the vacuum, and another vector called the Virasoro vector. So this is a infinite dimensional vector space. These things here are the vertex operators. So I will notate these slightly differently the way Jeff did, but it's a trivial change. This is the vacuum vector. And this is called the Virasoro vector. Okay, so V has this infinite grading. Okay, and the vacuum vector is contained in V0. And associated with each vector in this vector space is a vertex operator, okay, which is a way of gathering together an infinite set of linear operators acting on the vector space. So for U in V, we have Y, U. So in this context, Z is a formal variable, but later on when we actually apply these things, we'll see that we're going to get elliptic functions of various kinds. So Z can really be interpreted as being a variable on the torus. But for the time being, it's a formal variable in this setting. So we have UN Z to the minus n minus 1. So I'm using a round bracket notation to denote modes. Just note that difference in Jeff's. So I think so Jeff used UN. Okay, but okay. And what's the relationship between a given state and this vertex operator apart from that formal object there? There's this creation axiom where, well, if I act with y, u, z on the vacuum, okay, it's, well, how do I put this? It's u minus 1 acting on the vacuum plus order z, let's put it that way. So we have positive powers of z, okay, and you can see that from the definition here when I put n equals to minus 1. I have u minus 1, that's the z, the 0 term, and this is equal to u. Okay, so u minus 1 acting in the vacuum is equal to u. The so-called creation axiom. So by acting with the vertex operator for u on the vacuum and identifying the z to the 0 term, that's the actual vector of u itself that goes into this operator. The UNs, of course, are endomorphisms on the vector space. Okay, and the conformal vector generates a Virasoro algebra. So if I take the y of omega, so here I write the Virasoro generators in terms of Ln, and okay, it's no harm actually writing this in two ways. So in terms of notation here, this is the sum omega n z to the minus n minus 1, but it's useful to define Ln, which is formed by summing by shifting by 1 element to z. So that is Ln is omega of n minus 1. Minus 2 is, I always get mixed up, n plus 1. Okay, and then the Ln's form a Virasoro algebra. So this is one of the axioms, that there is such a vector, such that its modes form a Virasoro algebra. Of some central charge with central charge. So the central charge is sort of like an invariant of a VOA, some particular parameter associated with the VOA. Okay, and there's also associated with the Virasoro structure, then in particular, L minus 1 generates translations, and L0 describes the grading of the vector space. So just remind you of these facts. Oh, well, I've actually skipped one of the most important axioms, of course, which was localities. Let me, I'll come back to that in a moment. Well, okay, I'll finish off this part of it. So we have L minus 1 then, gives you a translation. Okay, again, this is described in jest notes, so I won't say any more about that. And L0 gives the grading. So L0 of u is equal to the weight of u times u, defines the grading. This is where my handwriting is degenerating, as I warned, might happen. So grading on V. So I call this conformal weight. So that is, so if u is contained in Vn, then L0 of u is equal to n u, okay, in this grading I talked about. Okay, and I left out then very important, of course, is locality. It's the most important in some senses. Property is that z minus w to the n of the commutator z is equal to 0 for n sufficiently large. For any pair of vectors u and v, if I take the commutator and the thing, if I take sufficiently, the commutator will vanish by multiplying by sufficiently high powers of z minus w, which basically means that when you take the product of these two guys here, there may be, in the expansion, there may be terms in z minus w which have negative exponents, but there's only finitely many of those. That's what that means. Okay. I'm sorry? I should say that, shouldn't I? Thank you, yeah. So, yeah. I do care. Okay, yeah. Okay, so now there are various properties, again, that Jeff talked about that follow from these axioms, and I want to highlight one or two of these. In particular, we have a kind of a commutator formula, which Jeff wrote down yesterday. And we also have an associator or an associative relation. In particular, I want to look at the commutator, which I'm going to write in the following way. So some properties. And again, as Jeff said yesterday, there are various ways in which the axiom can be set up. This is one of the problems with this area. There are almost as many axioms as there are authors. So just depending on where people started from, they axiomatize the VOA in a particular way, and then many of the textbooks spend many pages showing that all the various axioms are really the same. And so this is the set of axioms I'm going to work with, and I want to get on and actually do something with them instead of messing around with different axioms. So the properties we have are, one of them is that we have a commutator formula, that the commutator of a mode UK with a vertex operator. So I think Jeff wrote this down in terms of the modes of Vn, say, is the following thing. It's a very nice formula. I greater than or equal to 0. K choose I. Acting on V. V to the K minus I. Okay, and as Jeff was saying yesterday, this eventually terminates because UI, I forgot to say more about the gradient, didn't I? Well, okay, this will eventually terminate. And so it's actually a finite sum. For any pair u and v, this is a finite sum on the right-hand side. Okay, we call this a commutator. So in particular, if I choose u equal to the Virasoro, okay, and take v of weight v, then it follows that L0, the commutator of L0 with v, say taking the nth mode of this, I get the following standard formula. It's the weight of v minus m minus 1 So this tells you that if Vm acts on one of the graded vector spaces, it's going to raise or lower the grading by this amount. Okay. So hence, Vm acting on okay, I hope you can see it's bad notation. Easier to see in the printed version. Acting on the vector space Vn, okay, is contained in the vector space where the grading is shifted by this amount here. Okay, it's n plus the weight of v minus n minus 1. Okay. So the modes act on this interdimensional vector space by moving between the different levels. Okay, in general. And in particular, of course, we can choose a particular m where this term here, the shifting, vanishes, and that's called the level 0 mode. I should also mention, if there are any physicists here in the audience or people who have a conformal field theory background, the definition of modes here, again, probably Jeff mentioned this before, is a bit different to the definition of physics. In physics, the conformal weight will be included in here in this exponent. Okay, and that can lead to some confusion. So these are what are called math modes, mathematical modes, whereas as physics modes, you have to change the notation slightly and shift things. So I spent half my life trying to shift between these two different ways of doing things, but it's just a notational change, really. It's all, there's nothing more to it. So in particular, anyway, let me continue with this. And so for, if I choose m equal to, where's it gone to, the weight of v minus 1, then it implies that, well, I'm writing this badly, and define O of v to be this weight, the mode with this particular value, weight of v minus 1, then O of v is level preserving. It maps Vn, sorry, OVn that is contained in Vn. Okay, it's the so-called level, the level 0 mode, or the 0 mode. So the O is 0, if you want to think of this. This is called the 0 mode. So if you're using physics notation, this would literally be V of 0. If you have any background in conformal field theory, this would be called V of 0. Okay, but in math mode, it's V of weight of V minus 1. Okay, so this is a natural thing to work with, because what we're going to look at later on is when we come to looking at, after the break, I'm going to look at one-point functions and so forth. And so this is used to define one-point functions, which is the main subject of this talk. Okay, so I'm getting the main subject in the last 5 minutes. The one-point functions, which we define as a function of v and tau, and it's a trace over our vertex, over our vector space of O of v q to the L0 minus CO24. So this is a level preserving operator here. So it acts on each graded vector space here. Okay, and it's just a trace. So it's like a sum of characters you want for this operator acting on each finite dimensional piece of this interdimensional graded space. Okay, and then the power q keeps track of each of those grades. But the action of OV is just some linear operator acting on each of these finite dimensional vector spaces. And that's what we mean by a one-point function. So this thing here we're going to show for appropriate theories. Is a modular form. Okay. That's what so I'll do after the break is to show how you actually prove that fact, okay? And it's a very nice proof because it's completely constructive. And so it's one of these good theorems in mathematics that not only tells you an important result, but also tells you how to calculate, how to actually work out examples, okay? So it's not just some kind of like an existence theorem or whatever. It tells you how to calculate things. So, so I'm going to prove that theorem in some particular examples. Well, it's been fairly general, actually, generality to begin with. And then we'll do some specific examples where we make use of the theorem. And the basic theorem will involve computing a certain kind of recursive identity where various functions will arise, and the functions that arise will be, in this case here, these modular Eisenstein series, or I'm actually going to go to a slightly more general thing beyond, in order to get my hands on this, will also involve these where have they gone to now? These derivatives of P1, it's gone off the board. So all that stuff I was preparing at the beginning will then will arise naturally in the expressions that I'm going to compute after the break. Okay, so it's a good place to stop.